on Monday. All right, guys, so as you're moving back to your seats, I want you to write down this formula. We're going to describe it on his notes. Doesn't matter what color you get, you're out of colorful newspaper. So tomorrow you guys are going to be working predominantly on calculations of these equations. The heat energy related equations, there's only 2 of them, but there's one extra one that has a combination of 2 of them. So it seems as if there were actually 3 equations, but there's really only 2 equations. You're already exposed to one of them. This was it. Write this down for me, and I'll tell you what you're going to do tomorrow with this as well. This does not go on your colorful piece of paper yet. Just write this on some notes, okay? So let's describe each of these variables, because what you're realizing now is that heat and temperature are not the same, but they're related, so they must be related probably through a mathematical relationship as well. So this is the mathematical relationship. We call it Q equals MCAT. That is not an A, right? It's a delta T, but Q equals MCAT is how it's commonly referred to. What does this Q stand for? Shout it out. Heat, right? So you're writing down the variable, the name of the variable, and then the unit that the variable is generally expressed in. What unit is heat generally expressed in? Joules, right? So J for joules, right? What does this M stand for? Mass. And generally, what's mass going to be expressed in? Grams, okay? And then C, we'll get to in a second, okay? Delta T stands for, so change in temperature. And change in temperature is very specifically calculated. It's something minus something. Yes, T final minus TI, so T initial, right? So this is our delta T. And it has to be this way because sometimes we have a system that has gained energy. Well, if it gains energy, generally what happens to the temperature? What happens to the temperature if you gain energy? It's going to go up. It's going to get warmer. So then that's going to be a positive energy. So I'm gonna write that down here as well. So it comes in 2 varieties. If it's a positive temperature, that means likely it got warmer. And so I'm gonna call that an endothermic reaction or endothermic process. This is some old information that we actually kind of know a little bit about. And then if it's a negative value, what happened to the temperature? It decreased, and I'll tell you why. It decreased because it consumed its energy. So if you consume your energy, it's gone, right? If your energy is gone, you don't feel as warm. You don't feel as much energy. So you show that with a negative value. So it got colder, and so the reason it got colder. Oh, hold on. This is the endothermic one. I'm sorry, guys. I miswrote this. This is the one that's giving off energy. This is exothermic up here. Getting ahead of myself there. Yes, I'm getting ready to. So regardless, though, we're going to start talking about how does the delta T reflect the style of energy exchange, which is labeled either endothermic or exothermic. So notice, though, and I didn't ask this, what is the unit of our delta T here? Celsius. So this is when we're going back. We're going to stick with Celsius. So in our mind, we should keep gas laws in one compartment, and what's the temperature always established in gas laws? Kelvin. And then thermochemistry, which is what we're doing now, is always going to be Celsius. So that should be a big divide for you there. All right, so then you start to realize that these units are actually going to have to come together to form this new constant. You know how in the gas laws we had that R constant, which had all the units in the equation? Atmosphere, liters, moles, and K. This is the same thing. This is called specific heat capacity. Capacity. And the specific heat capacity, that C for capacity is why it's actually labeled C. It has units of joules per gram degree Celsius. Joules per gram degree Celsius. So that gives you a lot of information for one equation. And if you look on, go ahead and look at the lecture note sheet. that you just picked up. I've printed the concept for you as well. Do you guys see what it says lecture practice? Chapter 17, lecture practice. Yes? So this equation is going to be used for the first 4 questions. That equation is used for the first 4 questions. So yeah, you can pick up lecture sheet if you need to. But if you want to make a note of that, this equation is used for questions 1 through 4. You'll be fine. That's something that you'll be attempting tomorrow, though, in class, not at home. The second equation, and I have a couple of minutes to explain this. The second equation takes this and it compares 2 different materials. It compares something like what your simulation was comparing. Who got to the part where it asked to find the specific heat capacity of the metal? Okay, so this is where I saw hands going up. I was like, okay, I know what we're asking about. So what we have is we have a, I'm going to draw this is our system, and everything else around this, those are considered our surroundings. So in terms of energy, is energy lost? Is energy destroyed? Is it created? No. Okay, so what law can you state with all those kind of ideas mixed them together? Law of conservation of energy, right? So I always laugh when I read this little sticker on the lights. It's like, go green. If you're the last one, turn off the lights, please. Conserve energy. Jokes on you people. Energy's always conserved. It's just efficient to turn the lights off. There's a difference there. It is always conserved because energy is not lost or created. It's just simply transferred. So if my system is warm and my surroundings are cold, what's going to happen to my energy? Transfer into the system or out of the system? Out of the system. So if this is warm and this is cold, I'm going to say cold and like that because it's a lack of energy, we're going to transfer energy out. So if I transfer energy out of my system, is it gone? No, it's just in a different place. It's still conserved. So if I lose energy inside of the system and the surroundings, it has to gain energy because it can't just disappear. Who gets a positive Q value, a positive influx of energy? The surroundings get a positive Q value, positive heat value. Who's losing energy? Who's losing heat? The system. You get a negative Q value. So the Q values, though, the magnitudes of them, they're the same value. It's just showing if I'm negative, I've lost energy. If I'm positive, I've gained energy. But the Q values are the same because the energy is conserved. Give me a thumbs up if that idea makes sense. Okay, most of us are good there. So the idea is just that energy is conserved, one is losing, one is gaining. But I can't really do much with Q. I don't have a value for Q, but I can always collect information about the mass of a system and surroundings, the temperature start, the temperature final, and even I can look in a value sheet and look at the specific heat capacity. So the question that you guys were stuck on was Q is equal to Q. One is positive and one is negative. And for instance, it could be like system versus surroundings or vice versa. It just depends on which way the energy is flowing. But Q and Q equals something else. Q itself equals MCAT. So what we can do is replace MCAT into the Q variable place, and we can say MCAT of the system equals MCAT of the surroundings. Oops, right there. This information is called calorimetry. Whenever you set up with the system and surroundings debate here, it's called calorimetry, which if you look on your lecture notes, it's that second subset of questions. So what you're going to see is that we'll use a very similar version of MCAT, but a combined version too. So in this case, the question on your web quest is metal versus water. So I'm just going to say that the MC delta T, of the system itself is a little piece of metal that we're talking about, the metal here, equals MC delta T, but for the surroundings, which is a cup of water. So you're dropping like a penny in a cup of water. That's the system and the surroundings. And so the question in this particular example said, what's the C, the specific heat capacity of the metal? Well, the specific heat capacity of the metal is this guy right here. So I want to solve for that C. So in the simulation, it gives you information about each of the other pieces. You just have to pull the data from the simulator. So C over here, how do I get C by itself if I want to mathematically or algebraically redesign this equation? Divide by what?
of the metal, right? So I'm going to divide by M and delta T of the metal on both sides. And say it again. We're just going to mathematically plug the values in so it will work. So this M and this delta T will cancel, but it's not going to cancel over here because this is a different mass. This is regarding metal, this is regarding water, this is water, this is metal, so they're two different values. So we get C by itself for the metal equals this big guy, all this together, MC delta T for the water, divided by M delta T for the metal. And that's all I'm going to do right now for you guys, because I want you to see how this works in your simulator before I go through solving all the equations with you. You need to kind of touch base with that for yourself. So what's going to happen is tomorrow I have to go to an AYT board meeting. So I wanted to give you a glimpse at these two equations because I have my YouTube video that I'm going to have you guys watch and listen to with these two equations. So as you go through the video, you're going to solve most of the questions that go in section 1, 2, and 3 here. Not all of them, but you'll have to solve a couple of them by yourself. But that's all I'm going to have for you to do. So after that, please get together with your science center group or science in the box group and finish up those teacher and student procedures and even outline your video. So if you know that there's a little bit of time for that tomorrow, make some plans to have some things ready so you guys can jump into that after your video.
So the video for watch tomorrow.
Yes.
What do we do?
So in the video, it'll say you're going to make a foldable, and it will walk you through how to make the foldable, and I'll make it very clear for you.
Tomorrow?
Yes, in the video. So in the video, it's going to say make a foldable, and you're going to make the foldable with the colorful paper that's not like you have it now, and you'll have your equations to solve as well. Okay. If you need to get with your science in the box groups on the way out, drop your homework. Wait. Drop your, not all your homework, only the active reading, the close reading. And if you have comments on a separate sheet of paper, add that to as well, so staple it. However, you keep the reading guides until I want them later. The questions that you answer to the group goes in there as well, so make sure you're you can let this one read out, probably. Thanks. There's a couple staplers around, you just have to look